Dear students, today I am giving the 8th video on Topology 2, and actually this is the third section of Unit 2, and we are discussing here normal and completely normal spaces. In last class we have discussed regular and completely regular spaces. Here we are going to discuss normal and completely normal spaces. We start with the definition. A T1 space X2 is said to be a normal space or a T4 space, provided that whenever C and D are disjoint closed subsets of X, there are disjoint open sets U and V such that C subset are equal to U and D subset are equal to V. Last class we have studied the regular spaces, that is T3 spaces, moreover Tikno spaces. And here we are going to start with a normal space, that is what a T4 space. You already studied T0, T1, T2, T3 spaces, and this is next definition, that is T4 space. A T1 space X2 is said to be a normal space or a T4 space, provided that whenever C and D are disjoint closed subsets of X, there are disjoint open sets U and V such that C subset are equal to U and D subset are equal to V. Example, every matrix space is normal. And there's a question, prove that a normal space is always regular. That is, a T4 space is always a T3 space. Proof, let X2 be a normal space, that is a T4 space. Let C be a closed subset and P not an element of C. Then set P and C are closed subsets of X. But given that X2 is a normal space, therefore, by definition, there exist disjoint open sets U and V such that set P is subset or equal to U and C is subset or equal to V. This implies P is in U and C subset or equal to V. That is a definition of regularity, or X2 is regular, or X2 is a T3 space. One remark is given there, and normal spaces were introduced by Vattoris in 1921 and by Tietz in 1923. They were also studied independently by Alexandrov and Urison in 1925. The following is an example of a topological space that is not regular. Example is given there. For each A in R, let U alpha equal to set of X in R such that X greater than E. Put tau equal to set U alpha such that A in R union together with the collection R and phi, a whole set and empty set. Then clearly tau is a topology on R. Here there does not exist disjoint non-empty closed sets because no two non-empty closed subsets of R tau are disjoint. Hence, for every disjoint closed sets C and D, actually there does not exist such sets. There exist open sets U and V such that C subset are equal to U and D subset are equal to V. Here X2 is not normal because X2 is not T1. Therefore, the above space is not regular. Let C equal to set of X in R such that X less than or equal to 0, which is closed, and 1 is not an element of C. But we cannot find disjoint open sets U and V such that 1 in U and C subset are equal to V. Therefore, the condition for regularity fails, or R tau is not regular. Thus, the above space is not regular. That is also proved. Next theorem, a T1 space x2 is normal if and only for each closed subset C of x and each open set U such that C subset are equal to U. There is an open set V such that C subset are equal to V and V bar is subset are equal to U. I'll repeat that. A T1 space x2 is normal, necessary and sufficient condition if and only for each closed subset C of x and each open set U such that C subset are equal to U. There is an open set V such that C subset are equal to V and V bar subset are equal to U. You can discuss the proof of this. At x2 be a normal space, at C be a closed subset X and U be an open subset such that C subset are equal to U. Then C and x minus U are disjoint closed subsets of X. Moreover, x2 is normal. Therefore, there exists disjoint open sets V and W such that C subset are equal to V and x minus U subset are equal to W. Here, x minus U is subset are equal to W, which implies x minus W is subset are equal to U. V intersection W is phi, which implies V is subset or equal to x minus W, or V bar is subset or equal to x minus W bar, which implies V bar is subset or equal to x minus W because x minus W is closed. Or V bar is subset or equal to x minus W is subset or equal to U, or V bar is subset or equal to U. That is, there exists an open set V such that C subset or equal to V and V bar subset or equal to U. This is the first part. And conversely, suppose that x2 is a T1 space and for each closed subset C of x and each open set U such that C subset are equal to U, there exists an open set V such that V bar subset are equal to U and C subset are equal to V. We had to prove that x2 is normal. Let C and D be disjoint closed subsets of X. Now C intersection D equal to phi, which implies C subset are equal to x minus D. Then by assumption, there exists an open set V such that C subset are equal to V and V bar is subset are equal to x minus D. V bar is subset are equal to x minus D implies D is subset or equal to x minus V bar. Clearly, V intersection x minus V bar, that is equal to phi. That shows that x2 is a normal space. Next theorem, that is again important. A T1 space x2 is normal if and only for each pair of disjoint closed subsets C and D of x. There are open sets U and V such that C subset are equal to U, D subset are equal to V and U bar intersection V bar equal to phi. Similar theorems we have proved in the case of regular spaces as well. And here this theorem is for or the conditions are given for a normal space. A necessary and sufficient condition for normality is established in this theorem. It's an important theorem. Check it properly. Proof. First, suppose that x2 is normal, that C and D be disjoint closed subsets X, then there exists disjoint open sets U1 and V1 such that C subset are equal to U1 and D subset are equal to V1. Then by previous theorem, there exist open sets U and V such that C subset are equal to U, U bar subset are equal to U1 and D subset are equal to V, V bar subset are equal to V1. And we know that U1 intersection V1 is phi, therefore U bar intersection V bar is phi. Converse part, suppose that x2 is T1 and for each pair of disjoint closed subsets C and D of x, there exists open sets U and V such that C subset are equal to U, D subset are equal to V and U bar intersection V bar equal to phi. Here U bar intersection V bar equal to phi implies U intersection V equal to phi. Hence, normality follows. Next theorem, let C be a closed subset of a normal space X2. Then C tau C is normal. The subspace C tau C is normal. C be a closed subset of a normal space X2. Then C together with the subspace topology tau C is normal. That is what the theorem. Proof that A and B be disjoint closed subsets of C tau C. Then there exists closed subsets A1 and B1 in X2 such that A equal to A1 intersection C and B equal to B1 intersection C. Here A and B are closed next. Why? Because C is a closed next. But X2 is normal. Implies there exist disjoint open sets U and V such that A subset are equal to U and B subset are equal to V. Put U1 equal to U intersection C, V1 equal to V intersection C. Then clearly U1 and V1 are elements of the subspace topology tau C. Also, their intersection U1 intersection V1 is phi. They are disjoint. A subset are equal to U implies A intersection C subset are equal to U intersection C, which implies A is subset or equal to U1 because A is already subset or equal to C. Similarly, we can prove that B is subset or equal to V1. Hence, C tau C is a normal space. That is, the subspace C tau C is again a normal space. Next theorem, statement, let X2 be a normal space and YU be a topological space. Let f from X to Y be a closed continuous function that maps X onto Y. Then YU is normal. Let X2 be a normal space, YU a topological space, f from X to Y be a closed continuous function that maps X onto Y. Then YU is normal. We can discuss the proof. Let C and D be disjoint closed subsets of YU. Let f from X to Y be a closed continuous onto map. Then F inverse C and F inverse D are disjoint closed sets in X2 because F is continuous. But we know that X2 is normal. Therefore, by definition, there exist disjoint open sets U and V such that F inverse C is subset or equal to U and F inverse D is subset or equal to V. Now X minus U and X minus V are closed in X2. This implies F of X minus U and F of X minus V are closed in YU. This implies Y minus F of X minus U and Y minus F of X minus V are open in YU. Take M equal to Y minus F of X minus U and N equal to Y minus F of X minus V. We claim that C is subset or equal to M and D is subset or equal to N. First we are proving that C is subset or equal to M. Take an element, let X in C. This implies F inverse X is in F inverse C which is subset or equal to U. This implies F inverse X is not an element of X minus U, which implies X is not an element of F of X minus U. This implies X is an element of Y minus F of X minus U which is equal to M. Hence, C is subset or equal to M. In a similar way, we can prove that D is subset or equal to N. We had to prove that M and N are disjoint. So claim M intersection N equal to phi. If possible, assume that M intersection N not equal to phi. That is, you are taking an element U in M intersection N. This implies U in M and U in N. That is, U is an element of Y minus F of X minus U and U is an element of Y minus F of X minus V. This implies U is not an element of F of X minus U. and u is not an element of f of x minus v, which implies f inverse u is not an element of x minus u, and f inverse u is not an element of x minus v, which implies f inverse u is an element of u, and f inverse u is an element of v. This implies u intersection v not equal to phi. Hence the claim. Now we are discussing two definitions. First definition is completely normal space, and second definition is perfectly normal space. Okay, we can first discuss the completely normal space definition. A T1 space x2 is completely normal provided that whenever a and b are subsets of x such that a intersection b bar equal to a bar intersection b equal to phi. Then there are disjoint open sets u and v such that a subset are equal to u and b subset are equal to v. This is what a completely normal space. Next definition, a perfectly normal space. A T1 space x2 is perfectly normal provided that for each pair of disjoint closed subsets c and d in x, there is a continuous function f from x to closed interval 0, 1 such that c equal to f inverse of 0 and d equal to f inverse of 1. If it is possible, we call it as a perfectly normal space. Remarks. Completely normal spaces were introduced in 1923 by Tietz. Perfectly normal spaces were introduced in 1924 by Urizon. That's all about the second section, that is normal and completely normal spaces, and 7 pages notes are also given, and you go through the video properly, refer the notes, and any doubts means we can discuss in the next class.